Hiya. So in this video, we're going to look at an example of Poisson distribution or Poisson approximation more precisely. And I actually like this example. It's, in my opinion, a really fun example. So basically, we're going to look at a common human error. So what we're going to say is every single time you see a formula x minus y, there's a 1% chance you will copy it down as x plus y. Like this happens so often. So let's say it's 1%, right? This happens about 1% of the time. If you do 200 problems, what are the chances you will copy over 2 or more formulas incorrectly? So you're going to do 200 problems. What's the chance of getting 2 or more errors? So one thing to note here is every copy is independent. So every time you copy something, it's independent. We know that p is equal to 1 over 100. So let's write this down, 1 over 100, right? Because we have a 1% chance. We know n is going to be 200. Notice how np in this case is 200 times 1 over 100, which is equal to 2, which is close to 1. It's not too bad. But the expected value is 2. So we're expected to kind of fail 2 times. So let's look at the Poisson approximation. Well, the Poisson approximation tells us P of k exactly, right? P of k successes. And we want to know 2 or more successes. We want to calculate 2 or more errors, right? So what's a good way to kind of do this? A good way to kind of do this is, well, let's take all the possibility errors, 0 errors, 1 error, 2 error, 3 error, etc. And just we want 2 or more, so we can just remove the 0th and the 1st and keep those. So this is just going to be 1 minus p of 0 and p of 1. So let's just keep those, let's remove those two and keep the rest. That makes our life easier. So let's calculate this. 1 minus, we're using the Poisson approximation. So we get e to the minus mu. So here, let me rewrite this. E to the minus mu to the k over k factorial. So mu is 2, so we get e to the minus 2 times 2 to the 0 over 0 factorial minus e to the minus 2 times 2 to the 1 over 1 factorial. So in this case, we get 1 minus e to the minus 2 times 1, right? 2 to the 0 is 1, 0 factorial is 1, this is 2, this is 1. So here we would get a 2 for the second one. So we get minus 2 times e to the minus 2. So this is just 1 minus 3 times e to the minus 2. So here you can plug this into a calculator. And we get 0.594. So you have a roughly approximately, so this is, I guess I should say approximate here. Or no, this is okay. This is the approximation part. So we have roughly a 59.4% chance of making 2 or more errors. That's a pretty good amount of chance. Okay, so we looked at when mu is equal to 2. What happens when we look at different mu's? Like what does our distributions kind of look like? So here I'm going to give a couple different examples. I've already calculated these, so don't worry, but we'll look at what the different mu's kind of look like when mu changes. So mu here, remember, is equal to n times p. So we're keeping mu static for the Poisson approximation, and we change n, right? So keep mu static, and we change n. That's the big thing for this one. So here, if mu is static, what we end up getting is a distribution that looks like this. And you'll notice here it's very much similar to the graph I drawn above, right? So this kind of graph here. This black graph here on the left-hand side. Here I guess I should write e to the x. Here we have e to the minus x. Okay, cool. So for this mu, it's nice. For 1, we also saw this, right? So, and this mu is equal to 0.5 kind of makes sense, right? Like the expected value is basically going to be kind of in between these two, right? Which is kind of weird. If our expected value is 1, well, it makes sense that most of them is going to land between 0 and 1 times. So in this case, it kind of makes sense that our graph does a little thing and then it dips down like our exponential curve. Exactly what we would expect. When mu is equal to 2, here you can start seeing that it's looking closer to a binomial distribution, but it's still not quite there yet, right? So here we just get an up and then a plummet. So we don't really have this other half here, right? We don't have this little part here. So I guess maybe I should have done this in red. Let me do this in red. Right, we don't have this when mu is equal to 2. And so this is the kind of difference between normal approximation and Poisson's approximation. If everything is kind of chunked up near this beginning part and we don't have this nice curve, this nice bell curve, then it's probably better to use Poisson instead of the normal approximation. So yeah, so that's basically Poisson. And the next video we'll talk about random sampling. So I will see you then.